Very good. So I too am not a historian, as Peter Goddard said this morning. I'm telling about my own story of a period that actually overlaps very closely with Peter's. I was a graduate student and from 1963 till 67 at Stanford with my thesis advisor, Bjorkane, working in current algebra, which was one of the ways we avoided talking about quarks because quarks were not quite a legitimate thing, given their fractional charges, until we understood confinement, which was quite a bit later. So I then spent a postdoc at Daisy, where I did nothing very interesting, and returned to the Boston area, where I didn't have a job for a year. But mid-year, I came to Harvard and asked for an office because I was working with Tom Appelquist and Joel Premack. So I got involved in the period of the early development of the standard model. And then, again, following my husband, I used my Sloan Fellowship to be a visitor at Stanford in the academic year 76, 77, where Roberto Peccei was an assistant professor, and we started talking and working together, particularly around instantons, which were a new thing that introduced features to the gauge theory that nobody had thought about before, coming from Polyakov and 't Hooft. And this was the lead-in to the work I'm going to talk about today. So let's see, how do I advance this slide here? Not moving ahead as it should. What do I do to make it move? Sorry, I just need to figure out how to make the slides move ahead. If I go to this view, I can do it. All right. So Roberto Peccei was the one who asked the questions. And the question is one that comes about in the current presence of instantons, and I'll explain that. But the question is, once we know that there is CP violation in the weak interactions, how do the strong interactions manage to maintain CP symmetry to such a high level? And this, of course, is the question that led to our work, and our answer, I think, is still the best answer to this question, although there are other possibilities that people still are thinking about. I wanted to share a photo. Roberto is no longer with us. This is in 1991 at Aspen, where he led us on a long hike, and you can see 3 exhausted people following Roberto in the mountains of Aspen. I just wanted to give him the credit because obviously this work was a collaboration and he was a very important part of it, and he's not around to give his opinion on how it happened today. So a little background, and this is very standard particle physics, but since most of the audience here are string theorists, I thought it was worth reminding you of all these things because they're critical to understanding why the problem arose and what we knew and didn't know about it. There are these 3 discrete symmetries in field theories, and this is a talk which is purely field theory. Each of these individually and together have physical consequences, and we will talk about what those consequences are. The product of these 3, CPT, is an automatic symmetry in any field theory. It follows immediately from having a local Hermitian Lagrangian with Lorentz invariance. And so this also, in any theory which doesn't have a lot of different types of particles in it, enforces CP and T symmetry separately. And this meant that when CP was discovered in 1964 in experiments with K-mesons, it was a total puzzle to the field. There were no theories around at that time that could give it this kind of effect. what kind of effect violates CP? If you have two processes which are the CP conjugate of one another, in other words, you turn all particles to their antiparticles and all antiparticles to the particles, and look at the comparison of the rates for any process with that way. If CP is a symmetry, those rates have to be the same. Then there's another whole set of consequences where you have these peculiar particles, which are neutral mesons, but have two different flavors of quark and antiquark. Now, if CP is a symmetry, the mass eigenstates for those mesons must be CP eigenstates. If they're not, that's a CP violation. And that was what was discovered by Peccei and Cronin. Or you can have an inequality of decay rates if you make a state which is one of these mesons and it somehow mixes. So the states are produced. Let me go to the next slide. So here's the quark labeling. A K meson is an anti-S quark and a D, and an anti-K meson is an anti-D quark and an S. And then the other ones come with other flavors. You have other such possible neutral combinations. And the states of different CP, since CP turns a K0 into a K0 bar, the states of definite PC are admixtures of these states. The little mess with even and odd, under C, the first state is even and the second state is odd, but under P, both states are odd. So the first state is odd under CP and the second state is even under CP. And this was an explanation for the fact that there are two neutral K mesons discovered with very different lifetimes. Why are the lifetimes so different? Well, the K mesons, these neutral K mesons can decay, for example, into a pi plus and a pi minus. But if we talk about a spin zero parity negative particle decaying into two pions, only the state which is CP odd can decay into two pions, and the state which is CP even cannot, because the two pion state is a CP odd state. Therefore, the one which can't decay into two pions has to decay into three or more pions. And the phase space for that is much more limited. So the lifetime of the even state, the one which must decay into three pions under CP, is much longer. And that was a big puzzle that was explained by CP, and everybody was happy until Peccei and Cronin, in their experiments in 1964, looked at the long-lived kaon state and found that actually it did decay into two pions. So what they did is they produced the kaon beam, and they waited until all the short-lived kaons were gone, and then they looked for the decays, and they found some two pion decays. So they found that CP was not a symmetry of this theory, that the long-lived state had an admixture of the CP even piece, a tiny piece, but still definitely non-zero. And this was the puzzle. Because no known theory had CP violation in it. It's a quantum interference effect between two contributions to the same process with different complex phases of coupling constants. But coupling constant phases are not all physical. Many of them can be made real by simply redefining fields. In fact, even in the standard model, which has multiple particles, the original standard model had two generations of quarks and one Higgs doublet. That means it has lots of particles, but even so, all the coupling constants in that theory can be made real. You have to have more particle types than coupling constants. Or you have to have more coupling constants than particle types before you can finish up with a coupling constant phase that actually has physical consequences. And this was pointed out by Kobayashi and Maskawa, that you need at least 6 quark types or multiple Higgs fields to have CP violation in the standard model. So I'm going to go a little bit into the detail of the CP violation that is observed in the standard model. The quark types coupled to the W boson, one up type and one down type, so they're obviously different flavors, but any up type can couple to any down type quark. So there's a matrix of couplings in the standard model for quark weak decays. And when you make as many of the couplings real as you can, you find there's one phase left in this theory. You see this rho minus iota piece in the corners of the matrix, and you see the 2 by 2 matrix is totally real, which is the statement that a two-generation theory does not have any CP violation. So this was well understood by the mid-70s. Here's a history of measurements. So the little triangle in the middle, it's easiest to see in the first diagram. The little triangle is a representation of those coupling constants, a unitarity relationship between them that says the triangle closes, and each side and each angle of that triangle corresponds to some measurement you can make in the standard model. In 1995, we had a measurement only of one side of the triangle. So each color band here corresponds to some measurement in the theory and how it restricts that triangle. And you can see the upper vertex of the triangle is off axis. That means there's CP violation. The triangle is not collapsed. And then as we started to do B physics in the 2000s and on, you see the measurements get more and more precise, and the triangle keeps fitting all the measurements. That is a statement of the consistency of the standard model and the precision with which we understand the CP violating parameter in the standard model is the fact that that triangle has non-zero angles. So this is a history of understanding CP violation in the quark sector of the standard model. And that CP violation is part of the standard model theory. That means we cannot impose CP as a symmetry on the strong interactions, because the strong interactions are part of a theory which also has the weak interactions in it. And you can't impose a symmetry on part of a theory. You have to have the whole theory or none having the symmetry. So what that really means physically is that loop effects bring this weak CP violation to affect the strong CP parameters and induce a CP violating parameter. Even if you started writing a theory that didn't have any CP violation in the strong interactions, you would have it appear from weak interaction effects. Now, in QCD, what appears is this parameter of a totally antisymmetric tensor with two F variables. F is the same as it is in QED. F mu nu is d mu a mu minus d nu a. It's the antisymmetric combination of two Fs, which in QED, such a thing vanishes. But in QCD, because of the color variation, F has an additional term, which is a product of two A fields, not just a derivative of one. And so you can get a term here, which is non-vanishing, which is a product of three A fields in A0 equals 0 gauge. And that gives you, this was introduced. This term is CP violating. And there's an upper limit on the neutron electric dipole moment, which is tiny. The neutron electric dipole moment is a strong CP violating effect if it were seen, but it's never been seen. The upper limit is very tiny. And when you translate, as Bill Bardeen calculated, translating that limit on the dipole moment into the limit on this parameter theta, theta is very small. It's less than 10 to the minus 10. And so the question that Roberto was asking is, why is this parameter so small? How does the term arise? Well, if you think about QCD, there are gauge configurations which, so this is pure gauge fields, nothing else happening. This gauge configuration is equivalent to the vacuum. It's a gauge transformation of the vacuum. And yet it has a winding number. And an instanton is in fact a tunneling event where in a configuration with this number n of value 1 converts to a configuration with n plus 1. So if you like, n is kind of the number of instantons that have happened from field 0 to this gauge configuration. But that means these states are not gauge invariant. The gauge invariant state is a superposition of all these different n states. So the true vacuum of the theory is a theta vacuum, not an n vacuum. And this looks like an additional coupling term, but it's actually introduced into the theory in somewhat different ways. That number of instantons between the initial and the final state here is the quantity above, and that quantity is in fact the same thing as the FF dual I'd written on the previous page. So the theta term comes from instanton effects. Since CP is not a symmetry, we can't set it to 0 because the higher order effects will reintroduce it. So the question is, why? What makes it small? Can we find a theory where it's naturally small? Now, it's a little more complicated than that because the physically relevant phase is actually theta minus the phase of the quark mass matrix. Of course, we always arrange our coupling constants to we use field definitions, chiral field definitions, to make the quark mass matrix real. And before we were looking at QCD, we thought that had no effect. But the Jacobian of that change is actually a change of theta. So when we make a chiral rotation of a quark field, we change the value of theta. So that means any theory which had a massless quark, we could simply redefine the phase of that quark field and set theta to 0. In other words, in a theory with one massless quark, theta is an irrelevant unphysical parameter. But no quarks have 0 mass, so this is not the answer. However, we also knew that in the very early universe, in the hot early universe, the Higgs vacuum value is 0. All the quarks are massless. So that says in the hot early universe, theta is not a relevant parameter. So this had us very puzzled. We thought, how can it be irrelevant early on and relevant later? And we were thinking that, well, we'll just get rid of it in the early universe and then it's gone and we don't have to worry about it. So this is actually completely wrong because there are physical consequences of rephasing those quark fields. I'll come to that. But we actually tried to draft a paper and we had some draft that we were fighting over. Roberto and I were still not convinced, but we were trying to understand, how does this not work? And at that time, Steve Weinberg was a visitor at SLAC. So we went to talk to him about it. Before we told him anything about our ideas, he gave us a little lecture on CP violation and pointed out that when you change the phases of the fields, you have to worry about the couplings of the quarks with the Higgs particle. The very terms that give the quarks their masses have coupling constant phases. And when we change the fields, we change the definitions of those phases. That immediately showed me what was wrong with our puzzle, because then when the quark masses do appear as the universe cools, these Yukawa couplings are going to give you a quark mass matrix that isn't real. And making all the quark masses real will require these chiral rotations again, and will put the theta back into the theory. So in general, in the standard model, the problem exists, and it's not solved by the fact that the quarks are massless in the hot early universe. However, that told us what to think about. Because now the question becomes, okay, can we arrange the Higgs potential so that as the universe cools, it automatically falls into a state with theta equals 0? In other words, can we make the minimum of the Higgs potential be at 0 theta? Or rather, at that value of phase, so that when we make the quark mass matrix real, we finish up with 0 theta effective. And the answer to that question is yes. How do you do it? Well, you have to introduce another symmetry. This is a symmetry of the Yukawa couplings, and now called Peccei-Quinn symmetry. And it cannot be introduced into the standard model without adding additional Higgs multiplets into the theory, at least one more Higgs doublet and possibly more. So it's a symmetry of the Higgs couplings of the quarks and the Higgs, and it's spontaneously broken when the QCD field gets a vacuum condensate, which actually happens very early in the universe, before the phase. There's two phase transitions, one in which the QCD gets a vacuum value and one in which the Higgs gets a vacuum value. And the potential for that second transition is tilted to depend on theta once there's a QCD vacuum condensate. So I call it a pseudosymmetry because it's a broken symmetry, broken by QCD itself. But it's not a symmetry that you see in the QCD part of the theory. It's a symmetry that you see in the Higgs part of the theory. And it finishes up giving you the desired effect that the Higgs transition occurs if you've set theta to 0 by changing the fields. Then when the Higgs transition occurs, it stays 0. There's no phase of the quark mass matrix. So this was the trick we found. And the simplest model, as I said, adds one light pseudoscalar. Now, we wrote our paper showing this model, but we didn't do very much discussion of the model because we had a pretty good suspicion that it wasn't going to last long. There's a relationship between the couplings of this light pseudoscalar particle and the couplings of the additional Higgs field that we put in. And one could search for it. It has, so you can look for it in accelerator experiments. Actually, they're called beam dump experiments because you put your accelerator beam through a huge space that nothing can get through, and you look for something behind it. So it's like there's a mountain full of old ships, actually, that is shielding the surrounding area from anything coming out of the collision areas. You look behind that hill and see if anything comes through, because if there were this light pseudoscalar particle, it interacts very little with anything else, so it can get right through that wall, and then you can detect it if you think about what you could do, detect it at the other side of the wall. It also has astrophysical consequences. For example, if you have an additional light weakly interacting particle that's produced at the center of a star, it escapes from the star without interacting. It cools the star, so the lifetime of a red giant star, which is long, gives us a limit that says limits the parameters, and it also has cosmological consequences. And very soon, this initial theory was completely ruled out by additional new accelerator-based searches, that said, no, the particle we predicted in that version of the theory doesn't exist. So currently viable models have to add even more Higgs field. They have the same symmetry. They add not just 2 Higgs doublets, but also some singlets, or maybe even an additional doublet, and you can avoid these experimental constraints. So the general theory is viable, but the initial theory was not. Our second mistake was not taking our model seriously enough or thinking about the phenomenology seriously enough. We saw there was a light pseudoscalar particle. What we didn't see, and we should have, was that it was a generic consequence of our symmetry. It's a pseudo-Goldstone boson of the pseudo-symmetry. And so any theory that realizes our symmetry would have a light pseudoscalar. Its couplings are less constrained when we put more scalars into the theory. But the fact that this light particle exists in general was something that we didn't say. It was separately noticed by Weinberg and by Wilczek, and Wilczek called it the axion. Weinberg actually called me and asked, did you notice this? And I said, well, it took me about 2 minutes to say, well, no, of course, you're right. It's obviously true. It's general. But we didn't actually notice that we had that this would be the consequence of any model that had our symmetry. So that was a second mistake in our work. And I think my general argument is anything we do in physics, it's interesting to tell in the history the wrong paths we went down as well as the right paths, because young students look at it and think everything sort of arrives perfect. But of course it doesn't. We have to struggle through various versions of an idea before we get to the right version. Now, and very interesting aside to this is that dark matter could actually be made of axions. And recently, it's become quite popular to be looking for axions as the dark matter. For a long time, particle physicists were looking for supersymmetric heavy particles as the particles for the dark matter. But as searches for supersymmetric particles at CERN and other accelerator searches did not find them, that candidate became less attractive for technical reasons. The matches of parameters didn't come out so well. But the axion, which had been sitting around not being paid much attention to by very many people, although some had been working on it, it's a very light particle. I'll show you plots. It's fractions, milli electron volts, or lighter. So how can it be a dark matter particle? Because very light particles disperse faster than gravitational attraction clumps them. So small fluctuations of density in the early universe, say of very light neutrinos, do not explain dark matter because the particles move apart faster than they get pulled together by gravity. So you don't get the seeds for galaxies of overdense regions in the universe. But the axions are not produced thermally. They're produced in this phase transition, and therefore they're a condensate. So they're produced in some kind of coherent state. And therefore, that makes them a viable particle for dark matter, as was pointed out by Peccei-Quinn. So this is very active going on, and the experiments, after many years of hard work to make them sufficiently sensitive, are reaching the sensitivity of the models that followed ours that have a few additional Higgs particles called invisible axion models. So far, nothing has been seen. A very small part of the allowable mass range has been searched. This figure is, if you look at the bottom, you see electron volts ranging from 10 to the minus 12 to 10 to the 0. And you see that astrophysics rules out down to like 10 to the minus 2. and spins of black holes rule out the very tiny ones. So there's an existing allowed range for axions. And then you see the green bars and green bands are experiments where you're looking at a cavity with a very high magnetic field in the cavity. If a dark matter axion goes through that cavity, it can excite it by transitioning to a photon in interaction with the magnetic fields. And a small amount of energy is deposited. You need an exquisitely sensitive readout of the vibration of that high Q cavity and very sensitive readout to reach the necessary sensitivity. And these experiments have in fact reached interesting sensitivity in only a very small fraction of that allowed range. All the other color bars down below are proposed future experiments, or experiments, the first band is experiments that are actually being built, and then the ones below are totally speculative future experiments. And eventually, we will either discover axions or say, no, dark matter is not made of axions. Even if that is so, that does not rule out a solution to the strong CP problem. It simply rules out the idea that the axion could be, the QCD axion could be what produces dark matter. There are many interesting other applications of the idea of these pseudoscalar axion-like particles, Goldstone boson particles. And so people are searching for ones that are not in the range for the QCD dark matter axions as well as these. But who knows when or if this will ever tell us that dark matter is an axion. It would be exciting if it were, but it's not something that we can be sure of. So in sum, our symmetry, I believe, is still the best answer to the question, how come strong interactions can be essentially a CP conserving theory, even though they're part of a theory which has CP violation. And that answer persists even if dark matter is not made from axions. But I think it would be very amusing to find out that it is. And although you gave me an hour and a half for the talk, this is all the history I have to tell you. So I think we should stop here. I think my message is what matters in doing this kind of research is having the right question, and having been thinking about instantons and what their role is in the standard model theory, got Roberto and me to this question. We made some mistakes on the way, but eventually we got to an answer that I think is a good answer to the question. The other thing I think is the moral of the story. It's now more than 40 years later. I wrote this slide some time ago and put it in this talk and didn't correct it. And experiment is still searching, but because the theory was designed to make axions hard to detect because they weren't detected. That's part of the way theorists avoid being ruled out. But there's no reason to exclude the answer. It's just a speculative answer. And thank you. I hope that's interesting to everybody, and I'll take questions.
Thank you very much for the talk. If anyone has any questions, please go ahead.
Professor Quinn, thank you very much for your talk. Were there any other approaches to strong CP problem that that were historically considered? And
Yeah. So one approach was to say, well, CP is a symmetry of the Lagrangian. We'll impose CP on the Lagrangian, and we'll try to have all CP violation be a spontaneous symmetry breaking effect? That answer is an answer in principle, but it doesn't work out very well when you try to make the CP violation come from spontaneous symmetry breaking in the theory. You don't quite get the right match between all the parameters to fit that very precise measurement of the quark, the CP violation in the quark sector that I showed you. And
Please go ahead.
the other thing I would say, when you go to supersymmetry theories, there are lots and lots of CP violating parameters in the theory. And you have to artificially say, oh, the CP violation in the strong in the supersymmetric theory is exactly matched to what we see in the simple standard model quark sector, and not you're setting many CP violating parameters to zero in any supersymmetric theory to get what's called a minimal supersymmetric model. So the puzzle in supersymmetry theories is even worse.
I see. Thank you.
I was wondering if you could say something about what you did after this work. Did you continue working on this problem? What was kind of what was kind of after, I guess my question is?
Actually, I worked on lattice gauge theories for a while, trying to understand, how we can calculate strong interaction effects in the standard model. That did not lead to very productive. The lattice gauge theory has led to very productive things, but my work in that area was not particularly useful. Then I went back to CP and I worked on those graphs that, let me go back and show you well, it doesn't matter. Those graphs of the measurement of the parameters of the standard model mostly come from an experiment called the B factories. And that was David Hitlin was one of the leaders of that B factory at SLAC. There was also one in Japan. And I worked with the experimentalists to design the B factory to be able to test the theory and work with the theory of what possible observations could be made with that facility to test the standard model CP violation theory. That was a large fraction of my work in the last 10, 12, 15 years of my career. So I worked on CP violation in different ways, but no more on this particular set of ideas. Because they were there and there was not much you could do beyond wait around for the experimentalists to test them.
What was around the period where like the original model was considered unviable?
It was very short. It was like 3 or 4 years before there were small experiments at SLAC and at, I think at Fermilab, another one. Actually, my thesis advisor, James Bjorkane, got interested in an experiment about that time, and he was involved in setting up the experiment at SLAC to test whether these light particles that were in the simplest model, their parameters were fully defined and you could go look for them. As soon as you put additional Higgs fields in, you got more parameters in the theory, and there was a band of possibilities, which is what I showed you in the picture. But the searches became much more difficult. But the initial model was relatively easy to rule out experimentally, the simplest one. And we kind of knew that, which is why we wanted to, Roberto and I thought our idea was so interesting as an answer to the strong CP question. We didn't want to get bogged down in the phenomenology of the simplest possible realization of it. So we just wrote our paper with a brief mention of that only, and did not make the observation that there would always be a light pseudoscalar particle.
See, thank you very much. Are there any other questions?
Oh, I have another one about axions. What do you think of the current state of perhaps indirect observations of axions? Like if we can detect them um, conclusively in particle accelerators, maybe there is some evidence from astronomical observations like
There are no accelerator experiments for axions. Axions are searched for in dedicated experiments where we're making the assumption that the dark matter is all made of axions. And then we can say, okay, if the dark matter is all made of axions, and if they have a certain mass, then in this cavity, we have the sensitivity to detect them. So they build a special purpose detector, very shielded from everything else, very cold, and they just wait for a dark matter axion to go through it.
Oh.
And dark matter axions are going through you all the time if dark matter is made of axions. Dark matter particles, whatever they are, interact very little with ordinary matter, and therefore there are many of them going through us all the time. So all we have to do is find a detector that's sensitive to them, and we could see them. But since they don't interact very much, it's very hard to do that. So there's no accelerator experiments. There are a variety of experiments all built on the same principle, that if you have some region with magnetic field, then the axion can convert into a photon in that magnetic field. And so if you have a region with very high magnetic field and some very sensitive instrumentation that will show a very small amount of energy photon, very low energy photon has been produced, you could detect it.
I see. I apologize. I asked the question a bit incorrectly. I meant like I was going to ask about the conversion of axions to photons and like strong magnetic fields, and I was going to ask about if there is any observations, for example, of magnetars or something where we would see like excess photon emission.
Yes, so there are no observations. Nobody's ever seen an axion, but there are experiments that search, for example, for axions produced at the center of the sun, or for axions in other situations where you put a photon beam through some. If this is true, right, a photon can turn into an axion in a magnetic field too. So you go axion photon through a wall that it couldn't get through unless it turns into an axion and then turns back into a photon. So you've got two very rare interactions to happen. But so shining a light through a wall kinds of experiments are looking for axions, not the dark matter ones necessarily, but looking for axions that are produced by a photon beam. There are various other searches. There's lots going on in this field. It's very active at the moment. And that was what all those little blobs on the slide that I was showing. I can go back to the slide if you want to see it again, but where is it here? I have to go to my slideshow, I guess. There's some funny thing about changing views here. My screen. My screen sharing is paused. I don't know. I cannot find the slide. I'm sorry. I'm a klutz. But at any rate, there's many different ideas for searching for axions. None have been seen in any of these ways of looking. And that only means that they're in some range of coupling constants where it's very hard to see them. And it doesn't mean they don't exist, but it doesn't mean they do either. So just like string theory, there's no direct evidence for this answer being a correct answer other than nobody has a better one.
Thank you very much.
Yeah, I guess if there aren't any other questions.
I have a follow-up
Oh.
question. With
Go.
regards to so Dr. Quinn, thank you very much for the marvelous presentation. It was much appreciated. Just sort of following with the notion of evidence of axion or axion-like modes in physics, or at least in emergent properties and bulk matter. Are you familiar at all with axion modes appearing as insulation phases in topological insulators? And if you could speak maybe to sort of any potential interest or overlap with the cosmological models that you've seen with regards to emergent properties in with regard to the Berry phase in axion insulator modes.
I'm no expert on this. I have seen briefly the papers. I have been retired since 2010 and not being active in physics. So no, all that work is stuff that has happened more recently, and I really cannot speak to it. Ask Frank Wilczek to talk if you really want to know about other ideas of applications of axions, particularly the ones you're talking about there.
Thank you very much.
Okay, we'll be ending the talk here. Thank you very much for your time.
Yes, and I am sorry it was short, but that was all I had to say.
No, it's fine. I think we had it longer because in our experience it tended to go a bit longer, but we've had shorter talks as well. So thank you very much.
Good. Thank you. You're welcome. But